All right, so the main event today is we're going to discuss cache coherence. But before we get into cache coherence, let's finish up our discussion of Spark. You notice that instead of me teaching on Thursday, Kayvon did, and that's because originally we thought that based on when the programming assignments would be out, that you would need to know about optimizing DNN code on the GPU. But given that we've delayed the programming assignment 3 and so 4 is delayed, turned out that we didn't quite need the order of lectures, and so things are a little not as smooth as we might like, but nonetheless, you guys can context switch, right? All right, so back to Spark, right? So where we left off, we were talking about how to design a system for doing distributed computing on a cluster. And remember, the characteristics of a cluster, of course, is you've got separate nodes or servers that are connected by a network, and each of the servers is running its own operating system and has its own independent memory system, right? So, and the way that we communicate is by using message passing as opposed to shared memory. Okay, so the idea of in-memory fault-tolerant distributed computing, the goals of Spark are, what if you have an application that makes lots of use of intermediate data, right? So we know that we can make it fault-tolerant by using the map-reduce system. So what were the characteristics? How did we keep fault tolerance in the map-reduce system? Where do we put the intermediate data? Yeah, on the hard drive, right? On the distributed file system, the HDFS system, which we know is fault tolerant because it's replicated. But the problem, as we saw by looking at the system, it's slow, especially compared to the memory. It's 100x slower than the memory. And so the question is, can we, if we want an application that makes lots of use of intermediate data, such as a iterative algorithm, or a query where you've got the data in that you want to continuously make ad hoc queries to, then the map-reduce system is actually pretty inefficient, right? So how can we make something that's much more efficient but still keep our quality that we want in the distributed system as something that is still fault tolerant, right? And so the key abstraction we said was the resilient distributed data set, which was this read-only ordered collection of records, right? So essentially the sequence and the way that we get RDDs is we start with some data on the disk, on the HDFS, and then we apply transformations to it, right? So we can extract the lines from the text file and get an RDD called lines. We can filter, which is another transformation to get mobile views, and we can filter again to get Safari views, and then finally we can create a count from that, which is not a transformation, and so of course, so the result is a single scalar instead of an RDD. All right, and so we were looking at sort of how we implement RDDs, and we said that the problem was if you didn't do things efficiently, you could end up with huge amounts of memory for the intermediate data. And so of course, this course is all about improving parallel performance. And we said that parallel performance comes from, you've got to have lots of parallelism, lots of things to do at the same time, but you also have to optimize for locality, right? We've talked about a couple of mechanisms for optimizing for locality, and you just saw these used in the last lecture. One was the idea of fusion, loop fusion, right? And here, of course, we're trying to minimize the need for external memory access, and we're trying to improve or increase arithmetic intensity. And as an example, we saw that here in this example, and you saw it in doing attention, right? So Kayvon talked about flash attention, and that's essentially a combination of fusion and tiling, right? And so tiling was the other locality optimization mechanism that we talked about. And we said that essentially in order to get these sorts of transformations, you have to understand the application, because you potentially have to globally restructure things. And so the nice thing about the Spark implementation is that you have the ability to do fusion with RDDs, since you've got a set of bulk operations, these transformations on RDDs, and the runtime system, the Spark runtime system, can look at what is happening and optimize these things. So in this example, we've got these transformations to create lines, lower mobile views, and then finally an action to create how many. And what you'd like to do, of course, is implement it in a fused manner, such as this, in which you just fetch one line from the file system, and then everything else is kept in memory, and you only do it a line at a time, right? And so, so this is ideally what you'd want to create, and the Spark runtime system will do this for you, and it does it when it can analyze the transformations and determine that you have narrow dependencies, right? And in narrow dependencies, one RDD only the partition of what one RDD only depends on a single previous partition, right? For instance, the lower partition 0 only depends on the lines partition 0, and the mobile views partition 0 only depends on the lower partition 0, right? So you can imagine then that the runtime system can fuse all of these transformations such that you don't have any extra memory accesses or external memory access. So there's no communications between nodes of the cluster, and so everything can be fully optimized and run very efficiently. So the problem is that you can have transformations that have wide dependencies, right? And which would require communication between the different nodes in the system. So an example would be group by key, right? Where in order to determine the group by partition 0 for RDDB, you would have to communicate with all the other nodes in the system to get the data from the different partitions, from partition 1, partition 2, and partition 3, for example, right? So in this case, of course, you can't do the fusion, right, within a single node. And so, this is something that would have a lot of communication, right? So the question is, in what cases can you optimize operations like group by key? So look at this example in which we are trying to do a join, right? So you're going to join by key, and depending on how the RDDA and RDDB, which you're trying to join to create RDDC, if you didn't know anything about the RDDA and RDDB, then clearly you would have to communicate across all the nodes in the cluster in order to compute RDDC. Okay? So in what cases might you be able to get away without communicating? If you're trying to do a join, for example. So as shown here, you have to communicate. But could you imagine a situation where you didn't have to communicate? Yeah.
Like a specific key would be like only in partition 0 of RDDA and only in partition 0 of RDDB and not in like the other partitions.
Exactly. So that's this situation in which if you partitioned RDDA and RDDB such that the keys the common keys only existed in a single partition, then you would have narrow dependencies. Okay? So that is shown in the second example here. So, essentially RDD-A and RDD-B have the same hash partition, right? And so that's shown in this example, or this code here. So you have an explicit hash partitioner, right? And you've named it partitioner, and you use it to partition mobile views, and you use it to partition client info, right? Right? So when you do the join, then the runtime system says, hey, these two RDDs are being partitioned using the same hash partitioner, right? So it can detect that these are equal, and it will determine that there are only narrow dependencies, and then it will make sure that that you can do fusion. All right? Everybody follow that? Any questions? Yeah.
There might still be an imbalance of keys, right? Like one RDD has only a few keys, and the other one has a lot of entries with the same key.
Right. So there is this question of load balance, but to first order, probably load balance is less of a problem compared to communication. So that's a good point. All right, so now we have a way of sort of scheduling the computation for locality to improve performance and reduce the amount of memory required. Now let's talk about fault tolerance, right? So we said that, the whole goal of the Spark system was to give you high performance in-memory computation with fault tolerance, right? So then the question is sort of how do you maintain the fault tolerance? So remember this idea of lineage, right? So you've got these transformations, which are these bulk deterministic operations on RDDs, right? And so the lineage then, or the set of transformations that you apply, starting with the data load from the distributed file system, is the set of transformations, gives you a log of the operations you need to perform to get to any particular RDD, right? So you know that if you want to get to timestamps, you first load from the HDFS, do the filter, do another filter, and then the map. And so this list of transformations then is known as the lineage, right? So you've got a lineage is essentially a log of transformations that can be used to recreate any RDD, right? And we know what property did we say that RDDs had, right? They're read-only. And transformations are functional, right? Which means they do not mutate their inputs, right? So we know that it's always possible, given an RDD, to recreate it from the hard disk, from the persistent data that we know will never go away in the system because it's replicated across all the nodes in the system. Question?
So if we're we're not storing the intermediates, we're just storing the log we have. Right. So when do we actually, materialize all this data? Is it just we just do all the computation and then at the end we store whatever checkpoints?
So why do you want to materialize data? Because
at some point we need it, right?
Yeah. So some point in this case, what does the user want? Timestamps, probably, right? Does the user necessarily care about the intermediate data?
No, so you would just try to fuse as much as you can.
Right, you're going to fuse as much as you can, and not keep intermediate data that the user hasn't asked for. If the user asks for it, yes, so you got to provide it to them. But if the user didn't ask for it, it's intermediate, and it could potentially go away. The only issue is, what happens if you lose that intermediate data before you create the final result that the user wanted, right? Okay, so what happens if, in this situation where, oh, we're not done with the computation, but there's a node that crashes, right? So this is the example here. So we've got a set of transformations that give us a lineage that allows us to recreate any of the RDDs that we have in our computation. And, you know, in the middle of computing the timestamps, you know, node 1 crashes, right? So it crashes, and we lose the partition 2 and partition 3 of timestamps and mobile views. Okay, so now what do we do? Yeah.
It's just kind of like LFS, like you just rerun the log.
Rerun the log. So we rerun the log. We assume that the data exists somewhere else because it's replicated in the HDFS, right? And we have a log of operations, which is fairly coarse-grained, right? So it's not a huge number of things that we have to remember. And we reapply the log in order to create the partitions 2 and 3 of timestamps, right? And so we recreate that from the partitions of mobile views, and well, we start with lines, we get to mobile views, Chrome views, and then we recreate timestamps. Okay? So that's the way that we recover from a crash. Question?
First, where is the lineage, the log of the lineage, where is it stored? Is it stored on the master node?
Yeah, the master node is keeping track of the lineage. We assume that, you know, that's one of the nodes, and it's not likely to fail, or it may be replicated. Yeah.
One more question is, like if you like kind of like this is kind of like code, right? Like the lineage is basically a form of
Yeah, it's just a log of the transformations.
So is it like if you wanted to write like, you know, functions on your own kind of data, like if you wanted to like, you know, do completely custom functions, how do you do that here? How would that be?
Well, remember, you've got to live within the Spark world, which means is you have to do transformations on RDDs, which are functional, right? So if you do things that are non-functional, you start mutating your input, then you've broken the Spark abstraction, and things won't work, right?
But so if I have, let's say, like just a function that takes the input, use the output does not mutate the input.
So you've got a set. Your data type is RDDs. The set of things you can do are transformations. If you go outside that abstraction, you've broken things, and you can't. And Spark says, "Hey, you're on your own," right? Other questions? All right. So so then we have a way of recovering from crashes, and we get the nice thing about Spark, of course, is that you get to use memory. And you get the performance benefits of memory, but you don't lose fault tolerance, which is critical if you're doing data processing. So how much performance improvement do you get? Well, this is, the Spark paper when it came out, 2012 or something like that. They compared to Hadoop. And Hadoop is always a good whipping boy because it's so slow, right? And so in Hadoop, this is the case. They're doing logistic regression, right, which is a very simple ML operation, and k-means, which you're very familiar with because, of course, you've played with that. And so we see that Hadoop, the first iteration is 80 seconds, and subsequent iterations don't get much faster. And, of course, each iteration requires an HDFS read and an HDFS write. The Hadoop binary memory basically keeps a binary memory copy instead of a text copy, and so it's slightly faster on the second iteration, but still has to access the disk. And then Spark only has to do the HDFS read, doesn't do the write, just writes straight to memory, and so subsequent iterations are much faster. So Spark is significantly faster, orders of magnitude, at least 1, maybe 2, compared to using the disk, which is consistent with the performance, delta we saw in the bandwidths between the storage system and memory, DRAM and SDFS. Okay, so we also see k-means give you the same sort of performance benefit. But, as I said, Hadoop is easy to beat because it is kind of, using the file system so intensively. But, Spark has gotten a huge amount of traction in the data processing world, right? So it enables you to compose a bunch of different domain-specific frameworks together with this underlying RDD Spark implementation, which is it works pretty well, and so you can combine the transformations with SQL, so you can do database processing. There's a Spark MLlib, which has a bunch of machine learning operations, a library to do machine learning based on the Spark abstraction. So of course you can use distributed clusters and get all the benefits of the Spark system while doing machine learning. And there's also Spark GraphX, which adds graph operations to the Spark ecosystem, right? And in previous versions of this class, you did graph analytics, breadth first search, right? Made you do. You don't do it this quarter. There's no breadth first search, right? Right. Yeah. In previous iterations, you had to do graph analytics operations, and so you might have been more familiar with the sorts of things that are in GraphX. All right. So in summary, then, Spark introduces this idea of the IDD as its key abstraction, and the observation is that using HDFS as a place to put intermediate data when you're trying to do these iterative kinds of computations, or when you're trying to continuously modify or query a particular set of data to do data analytics sorts of operations. The HDFS does not work as a good place to store intermediate data, and so RDDs are a much better idea, and they can be used as a mechanism for creating fault tolerance, because you've got these transformations, which are these bulk deterministic functional operations on RDDs, and they can give you a log that you can replay whenever there's a failure, and you can make sure that you can both get high performance and fault tolerance. Okay? And as we saw, Spark can be extended beyond the set of things that we showed in terms of transformations and actions to do all sorts of things like graph analysis and database operations. So one thing to be aware of is that scale out is not the whole story. So scale out was invented because people wanted to be able to analyze data that would not fit in the memory of a single server, right? So how much memory can you put on a single server today? Somebody give me a number? Typically, what might you see in a large server? How much memory? Gigabytes? Terabytes, right? So maybe 1/2 to 2 terabytes of main memory on a big server, right? So there are a lot of studies showing how Spark could be used, but the data sizes weren't really big enough, right? 5.7 gigabytes for this Twitter graph, and 14.72 gigabytes for this synthetic graph. And so if you can fit your data in memory, then you don't want to use the distributed system to operate on it, because you're going to have a lot of overheads. And so that's what this table is showing. It's showing that for 20 iterations of PageRank on these graphs, which fit in memory, you can run Spark on 128 cores, and you're still, 2 times slower than running on a single thread. Okay? So clearly, if the size of your data, does not demand using a distributed system, then clearly you don't want to use it, right? And so there's a researcher called Frank McSherry who kind of really took aim at the distributed systems people. He has this quote, right? He says, published work on big data systems has fetishized scalability over everything else. And basically, he says, they've been creating all these overheads and then, coming up with mechanisms to reduce the overheads which they have created, right? So he's arguing for let's look at performance as the metric instead of just scalability. So it's an important point, but the point is that you don't want to use these distributed systems if the size of your data doesn't call for it, right? So if you've got hundreds of terabytes of data, then the only way that you're going to be able to process it is by using a distributed system. But if you just have less than a terabyte of data, then a single system is going to be much more efficient. So keep that in mind. Any questions? Yeah.
What's the definition of scale out?
Scale out is as we've been describing, where you've got individual servers connected by a network, right? So there's sort of 2 dimensions to scale. People say scale out is when you are connecting nodes together by a network, and scale up is when you are connecting multi-cores together in a shared memory system. So until now, until the discussion of Spark, we've been basically talking about scale up, right? Where we are, thinking about how to program multiple cores that are sharing a memory. So if you share a memory, it's scale up. If you're not sharing memory, it's scale out. All right. So now let's change our topic to the main topic of today, which is cache coherence, which is a very important topic because it both has performance ramifications and it has correctness ramifications. And it's important from the point of view of software developers because you need to think about how you write your programs in the face of cache coherence. So how many people here have heard of cache coherence? Oh, good. How many people here know about cache coherence protocols? Okay, good. All right, well then you can help me teach the class. All right, so cache coherence. So if you look at a modern processor like the ones in your myth machine, you'll see that a large fraction of the chip is cache. 30% or more is cache. And we've talked about the importance of caches and locality in getting performance because, of course, if you have to go outside the chip to access the data that you need, it's going to take you hundreds or maybe, on very modern chips, several hundred cycles. And, if the CPU is stalled while this is happening, then, of course, there's a lot of time that you waste and your performance is not going to be that good. All right, so let's return to, I think, Kayvon's first or second lecture, which was on this cache example, right? And so we're looking at an array of 16 values in memory. And we said that we were going to divide the memory addresses into cache lines, okay? So cache lines are multiple bytes or multiple words that are contiguous or consecutive addresses in memory, okay? And lots of reasons that you want to have cache lines. But one of them, we said, what was one of the reasons that you wanted cache lines? Yeah.
Spatial locality.
To exploit spatial locality. That's one of the reasons you want cache lines. Okay. The other reason you want cache lines is it helps you do the implementation of cache coherency more efficiently, and it makes use of the data paths within the memory system because you move whole cache lines, and moving things in bulk is more efficient than moving things one at a time. All right, so we talked about, we defined what was a cold miss. It's a cold miss. Somebody back, yeah.
When it's for the first time, you haven't loaded anything in.
The first time that you access an address, it cannot be in the cache, right? So the cache is said to be cold as far as that address is concerned, so it's a cold miss. All right, so then we get access 4, and we get another cache miss. We talked about spatial locality. So while we're on the topic of spatial locality, architects think about hardware mechanisms to exploit program behavior. So what kind of program behavior leads to spatial locality? Yeah. Sequential access? Where?
Like for example, I'm not going to use like one and then.
Exactly. So that's sequential access. Where's the other place that you see spatial locality? Yeah. In the instruction access stream. So both in data and instruction, you're going to see spatial locality, and it's exploited by having a cache line. Okay, so we said cold miss. Then temporal locality is the other type of locality. Where might this exhibit itself in program behavior? Temporal locality, yeah.
The counter variable, how we access all.
Yeah, the counter variable that you keep accessing, maybe stack accesses when you're doing a recursive function, right? So repeated access to the same address is temporal locality, okay? So we said that we had cold misses, and then at some point in this cache, we needed to replace something because we had run out of places in our cache. And I think this was mislabeled a conflict miss, but it was actually called a capacity miss, right? If we had a bigger cache, we could contain 3 or 4 cache lines, but we can only have 2 cache lines, and so we have to replace one, and we have a capacity miss, right? So we have 2 types of misses, cold misses and capacity misses, okay? And now let's talk about a third type of miss. There's a miss model that was created by a researcher named Mark Hill, and it's called the 3 C's model, right? So you've heard about cold, you've heard about capacity. Now let's talk about the last, which is conflict, okay? So in order to talk about conflict, let me introduce roughly the design of the Intel Skylake chip, which is the chip in the Myth machines, okay? So it's got 3 levels of cache. L1 data cache, which is 32 kilobytes in size. An L2 cache, which is per core, so 4 cores. The data cache is private per core. The L2 cache is private per core. And then there's a ring interconnect, which is, as you might expect, is a ring, right? That connects all of the different L2 caches together, and they connect to a shared L3 cache, which is 8 megabytes in size. Okay, so what do we mean by a conflict miss? Well, it turns out that in order to simplify how you find things in caches, you limit the number of places that any line could go. This is called associativity. So the L1 cache here in the data in the Skylake chip is 8-way set associative. And that basically says that I only need to look in 8 places for any particular line, okay? So in this case, our line size is 64 bytes. So if I have a 64-byte line size, a favorite thing to do is sort of cache arithmetic, right? Which says, okay, if I've got 64 bytes in my cache line, how many lines do I have in my 32 kilobyte cache? 512, right? 512 lines. Okay, so if I have 512 lines in my cache, then a fully general way of finding lines in my cache, I would have to look in 512 places at the same time. Okay, this is expensive. Okay, and so to make it less expensive, I'm going to limit it to 8 places. However, the difference between having a cache where I can look in 512 places versus 8 places is going to lead to more misses. These misses are called conflict misses, right? So conflict misses are the extra misses you get because your cache is not what is called fully set associative, which means, a line could go anywhere in the cache, right? In this 8-way set associative cache can only go into one of 8 places, okay? So now you know about cold, capacity, and conflict. Okay? Yeah?
Is that to say that you're only going to ever store 8 lines in the cache?
No. It's just saying that there's only 8 places any particular address could go. Right? So I don't have to look all over the cache. I only have to look in 8 places. Turns out it's cheaper to look in 8 places than 512 places. Okay? That's the intuition. We could go into details, but that's the intuition. Yeah?
If you have this 8-way set associative, does that mean there's 8 buckets? Kind of
Yeah, 8 buckets. That's a good way to think about it. Yeah.
Does that mean that would it be rare for it to get to 100% utilization if that's the case? Or?
You mean some of those buckets could be underutilized? Yeah. Yeah, potentially. Yeah, but usually not. Yeah.
So one question is that so basically you're saying that the cache itself is kind of free, you're kind of branching out and then you have things inside the cache. Is that right?
They're buckets. They're 8 buckets.
Yeah.
And basically you look at the address and say which bucket you're going to go in, right?
Got it. So when you have larger and larger caches, do you have multiple levels of these buckets?
No.
You don't need them?
No. You're still going to do it. You're still going to look and have a way of. Usually, you just have one level of set associativity, right? You don't have multiple levels, right? Unless you've got another level of cache. Yeah. This is kind of weird, actually, because what you'd expect is as you get bigger, the set associativity should increase, but it starts with 8, goes to 4, and then goes to 16. It's kind of strange. Don't know why the designers did it that way, but that's not what you would typically teach. You'd say, hey, as you get bigger, you get more set associative, right? Because you're trying to. Because remember, higher set associativity means lower conflict miss rate, right? Because as you increase the set associativity, you're going to decrease the miss rate. All right, so let's talk about cache design. So you've got a line in the cache. There are 2 pieces to the line. One is the data, right, that is going to be contained in the cache. And the rest is the metadata, right, which basically tells you about the context of the cache line, right? So a key part of the metadata is the tag, which is essentially the address of the data, right? So you got this data from memory, and you need to know which address is, which cache line, sorry, which memory line is in the cache, right? So the tag is going to tell you that, right? And then there's a dirty bit which tells you about whether the data in the cache has been modified or not. And so in this example, we are going to write 1 to integer x, which exists at the address shown there, hex 1, 2, 3, 4, 5, 6, 0, 4. And the 4 indicates that, it's the fourth element that's the address of the byte in the line. Okay? Right, so reading from caches is fairly straightforward. Writing is a little more complicated, because writing's always a little more complicated. All right, so there's 2 types of writing. Can anybody tell me the difference between a write-back cache and a write-through cache? Yeah.
With the write-through cache, you always write back to the main memory. And with the write-back cache, you only update the value in the cache itself and then postpone the committing to the latest stage.
Exactly. So write-through says when we do the write to the cache, we also write to the main memory. And write-back says we only write to the cache. And later, the data is actually written to main memory. Because after all, you want to write to main memory. That's the whole goal, right? The cache is just this intermediate storage buffer. What about write allocate versus no write allocate? Does anybody know what that is? Yeah.
With write allocate, like when you write, when you have a cache space, you load it into the cache and then you write it. With write allocate, you don't cache space,
right. So the question is, what happens when I write to the cache and the line that I want is not there? Do I allocate? Do I actually fetch the rest of the line and write into the cache? Or do I just write directly to main memory? Okay. So with that in mind, let's look at an example where write allocate, write back, cache on a write miss, and I'm going to write to 1 to the address x. So what happens? So the processor performs a write, but it misses in the cache. The cache selects a location. If there's a dirty line currently in the location, then of course, what does the dirty bit indicate about the data in the cache line? Yeah. It's different than what's in memory. It may be the only place that this data exists in the memory system. Should we lose it? No, we should not lose it. And to make sure we don't lose it, we indicate that it's dirty. And then when we replace the line, we know that we can't just drop it on the floor, that we need to write that data back to main memory. And so that's what we do. And then since this is write allocate, we need to, allocate the line. We need to go get the data from the main memory, but we know that the data in the main memory is not up to date. So of course, once we bring that data into the cache, we then write the data, in this case 1, and then we set the dirty bit to 1. Any questions? Yeah.
Could you just explain again, sorry, the write back versus write through?
Yes, write back versus write through. So write back is this example, right? Where we had a miss in the cache, and we so write back versus write through. I was thinking allocate. So write back versus write through. So write back says I'm going to write into the cache and set the dirty bit, right? And then later that data is going to be written to memory when the line is replaced. That's write back. Write through says when I write into the cache, I also write to memory. And so that means I don't need a dirty bit, right? Because I know memory's up to date at that point. All right, so the shared memory abstraction, right? We said that essentially what we're going to do is we're going to share, we're going to communicate, and yeah, question.
Yes, sir. You saw the previous slide. I had 2 questions. Just what was step 4 again? Whole cache line is special feature that's rotated.
Yeah. So remember, it's allocate. So allocate means that we want to allocate, well, on a miss, we are going to allocate a line in the cache. So of course, we only have 32 bits of data that we're writing from the processor. So what about the other words or bytes in the cache line? Those have to be updated. Those have to be valid, right? So we have to go and get the data from main memory. Essentially, you perform the read, right? As if you were doing a read miss. So you get the full context of the cache line, and then you update the particular word that's being written by the store.
And how's that different from 3 cache line for memory? So is 4 the update and 3 is just the load into the cache?
Yeah. Oh, loads line from memory. Yeah. It seems a little redundant. Yeah. So loads line from memory. Yeah. Okay. So maybe we do this to make it right. Is that better?
Just one last question. What was the tag again? Sorry, I just missed the...
What was this? Tag?
Yes.
So tag essentially is the address of X. Goes in here. Address. Right? So remember, how do you know what's in the cache? Right? It's not... It can't have all the contents of memory, right? So you need to tag the cache lines and tell to tell the system what data is in the cache, right? Yeah.
Is there anything other than the dirty bit in the state?
Yeah. We'll get to that. That's the topic of the rest of the lecture. Yeah. Yeah.
Is the tag the address of X or the address of the cache line to X?
What do you think? No, it's the address of the memory, right? The address of the cache is kind of unimportant, right? It's an array, but what's it? The way to really think about caches is they're content addressable arrays, right? And the contents that you're after is the tag, right? You're saying, given an address that gets generated from the processor, does the cache contain it, right? So essentially the action that's going to happen is I'm going to take the address that was generated from the processor and I'm going to compare it across all of the tags in my cache, right? And if any of them match, or typically one, not more than one, then I'm going to say, hey, I've got a hit, right? So, do I really care about the particular address of the location in the cache? Not really, right? I only care that it has a tag for the data that I'm after. Yeah.
But if you address like memory that's right adjacent to the one in the tag, that might still be in the cache line, by the way, because it's a contiguous bit of memory.
Yeah. So I've kind of glossed over a bit, in that this is not the address of X, it's the address of the cache line, right? Because if it were the address of X, then how would I be able to exploit spatial locality? So every address that falls into this cache line is going to be represented by the tag, right? And you basically just drop off bits from the address in order to get the address that actually goes in there. Yeah.
So, like, isn't that sorry, just going back to the associativity, like, a particular section of tags are supposed to go in a particular like bucket.
I said we could go into details here, but believe me, they're not necessary. We can talk about it later. Yes, there's this whole set of things that you have to do to actually get the data, right, and actually do a cache lookup, and that has to do with set associativity. But as I've explained it here, we won't go into the details, but the thing to remember is that higher set associativity will give you lower miss rates. And that the higher the set associativity, the more difficult it is to do the lookup. All right, good. So we said essentially that shared memory programming, thread-based programming, is we're going to share addresses, we're going to make sure that we access the data when we want to properly using synchronization. And now we want to talk about sort of, how we expect the shared memory multiprocessor to behave, right? So we're going to read and write to shared variables by the processor is going to issue loads and stores, right? And so if I said, hey, here are a bunch of processors. They communicate over some interconnect to memory. How do you expect these processors to behave, right? And your intuitive answer would be something like, well, if I store a value to a variable x, and I then, on one processor, and I load that value from another processor, I should get the last value that was stored to that variable. Okay, and so that's kind of intuitively what you'd expect a shared memory multiprocessor, the way you'd expect it to behave. Okay, so the problem is that once you introduce caches into the system, now you have more than one place that the data or the addresses in the memory system can be, right? So, if you have any particular memory location, you can now get into trouble, right? So in this example, we've got these processes with their individual private caches, and they're connected via an interconnect to the main memory, and we have a variable foo, which is stored at address X, right? And so let's track how the processes access this variable, or the variable foo at address X. So processor 1 loads X, and it gets a cache mix, and so it goes to memory and gets the value, and so now there's 0 in processor 1's cache, right? So abbreviation of cache is, of course, $. Okay? And then processor 2 does the same thing, also gets a cache miss, and gets the value 0. Okay, now processor 1 does a store to X, says, hey, cache hit, I'm going to update, is a write back cache, I'm going to update my value of X to 1. Okay? Then processor 3 does a load of X, and it gets a cache miss, goes to memory. It also has a value of 0. Okay? Now processor 3 does a store of X, and it says, hey, cache hit, and now the value is 2. And processor 2 does a load of X, and then gets the value of 0 because it's got it in its cache, and it's a cache hit. And then processor 1 does a load of Y. Let's suppose we only have a single entry in our cache, so we have a capacity miss, and so it gets so it gets replaced, right? And so the value that it had goes back to memory. Okay, so now we have in our memory system the value of x in memory is 1, the value of x in processor 3's cache is 2, the value of x in processor 2 cache is 0, and processor 1 does not have the value address x in the cache. This looks like a disaster, right? Okay, so this is not a memory system that we could use. And so the question is, could we fix this problem by using locks? No, we can't fix it by using locks because fundamentally the problem is inherent to the fact that we've got multiple places in the system that have addresses that correspond to memory, and we have multiple places in the system that are changing those addresses. Okay, we have multiple processes changing their private copies of the addresses in the memory system. Okay, so how do we fix this problem? So we have a memory coherence problem. As I said, what you want intuitively is that reading the value and address x should return the last value written by x. But because we've got the main memory being replicated by local storage and processor caches, and then we have updates to these local copies sharing the same address space, we get incoherence. Okay? So, you can get incoherence even on a single CPU system whenever you have places that have a situation where you have multiple places that you can read or write from. So, for example, in a case of an I/O card, if the I/O network card delivers data into a message buffer using direct memory access, it could happen that the addresses in the message buffer are also in the cache. They could be stale in the cache, right? So stale because they've been updated in memory, and those updates have not been reflected in the cache. So this happens rarely enough that you could probably fix it using software mechanisms, right? So the software could flush all of the entries in the cache corresponding to the addresses in the message buffer, for example. Okay, so you could solve it with software, and this might be a reasonably performance solution given the frequency of occurrence of I/O. But if I'm actively sharing memory with multiple processors, doing things with software is not really a solution. So the question then is, we talked about this intuitive notion that I should get the last value of any address that was written by some other processor in the system. So the problem is, what exactly does last mean, right? So what if two processors, write at the same time? Who should be which processor should be the last? What if a write from processor 1 is closely followed by a read of processor 2 such that it doesn't have time to get that value? How do we make sure that this situation works correctly? So in a sequential program, last is determined by program order, right? And so this is also the way that we want to think about the ordering in a thread of a parallel program. Okay? And now we need to think about how these threads values, or these thread updates are going to be interleaved, right? So the way to think about coherence is, coherence, remember, is just talking about a single memory location or maybe a single cache line. So for any single memory location, we want to serialize accesses to that location such that, for any write, in this case P0, writing value 5, if in the serialization the P1 reading comes after the write, then it should get the value 5. And P2 comes after that write, so it should get the value 5, and so on. All subsequent reads should get the value 5 until P1 does a write of 25, and then all subsequent reads should get the value 25. So you have to be able to serialize access to a particular address such that you can, and the notion is that the reads and writes should, for any particular thread, should occur in the order issued by the processor. Okay? And then the value that you read is given by the last write in the serial order. Does that all make sense? Okay, so that's kind of what behavior that we'd like to see. And the question then is, how do we get the serial order, and how do we make sure that you get the right values from reads to writes, right? So one way to provide coherence is to think about it in terms of invariance. So what invariance do I want my system to hold, right? And so there are two invariants that are important. So for any address X or any cache line address X, we want to have a single writer, multiple reader invariant. So this means at any point in time, you are in a read-write epoch where there's only one processor that can change the state of that cache line. Okay? So read-write epoch, only one processor can change the state of the cache line. Or you're in a read-only epoch where any number of processors can read that cache line. Okay? So single writer, multiple reader. Okay? That's the first invariant. The second invariant is called the data value invariant. And this just makes sure that the value that was written in the last read-write epoch is what every subsequent reader will see. Okay? So in this example, address X, we have a read-write epoch. P0 writes to address X, and then the following read-only epoch, the value that was written by P0 is the value that is seen in the read-only epoch, right? And then we have a read-write epoch where only P1 can write, and then the value that is written by P1, or the last value written by P1, is the one that is seen in the read-only epoch following the read-write epoch. Yeah?
Does that mean we have to implement some sort of flush or switching between read-only and read-write?
Yeah.
Yeah.
Well, we will switch. We could flush, but there may be slightly more efficient ways of doing things. But there has to be a mechanism of switching between read-write epochs and read-only epochs. So that part of the U intuition is exactly right. Yeah?
The previous comment made about locks and cache coherency, right? It feels like if you have multiple processors accessing the same or writing to the same point, the same address in memory, you should anyways be having some kind of locking mechanism, right?
Yeah.
I guess I'm having trouble visualizing why this is still a problem if if when you're doing these kinds of parallel writes,
Well, it is possible for me to say you can write and he can write and you can write and can't all do it at the same time, but you could still have an incoherent system in that he could write to his own cache and you could write to your own cache and she could write it to their own cache, and you still have an incoherent system even though it was synchronized, right? Yeah. So the two issues are independent, right? One is a function of the fact that you've got multiple places the data can exist, and that is kind of inherent in a cache-based multiprocessor system in which you are caching shared data, right? So you can imagine a system that did not cache shared data, and you wouldn't have a cache coherence problem. What problem would you have? Yeah.
Every memory access would have to go to
A performance problem, right? You have a performance problem, but you wouldn't have a cache coherence problem. But yeah, so every reference would have to go to every shared memory reference would have to go to memory, right? And maybe say, I would design a very careful system to minimize the amount of shared data, but you're kind of this is not a useful system, right? Okay. All right. So how can you implement coherence? Well, there's some software-based solutions. You could try and do things on the granularity of virtual memory pages and make use of the operating system, but it would be slow, right? It'd be slow, and you'd also have a problem that we're going to talk about later, which is called false sharing. So what you want is a fine-grained hardware-based solution based on cache lines. And so we're going to talk about two different ways of doing cache coherence or fixing the cache coherence problem or implementing cache coherence. One is called snooping, which is a classic way of implementing cache coherence. And then the one that is used most often today in most systems is a directory-based system. Okay, but we're going to start with snooping since I think it's slightly more interesting and easier to understand. Okay. All right. So we have one way of dealing with cache coherence is kind of back to not having separate caches, having a single shared cache, okay? And so what would be the problem of the single shared cache? Yeah. Performance, right? So you have a bandwidth bottleneck because all of these processes are trying to hit the same cache, and you've got a limited number of amount of bandwidth you can gather the cache. And so you might be able to do it for a couple processes, but if you wanted to scale a number of processes, you would quickly run out of bandwidth, or that cache would be extremely expensive. The other issue is that what if the cache contains data that is not being shared? Then you can imagine one processor conflicting or having capacity misses caused by another processor. Okay, so this is called interference or destructive interference. But you can also have constructive interference. So imagine you had a for-all loop like this in which you had the iterations interleaved across the processes, right? So in this code, you can imagine that iteration I would fetch the data associated with the following iterations. Assume that you didn't have you had cache lines that were small, say one word, just for the sake of argument. So you can have constructive interference as in addition to destructive interference. Okay, so shared caches don't really work that well for level 1 caches, but you can use them for level 2 caches. So this is a processor I designed many years ago. called the Sun Niagara 2. And it had a shared cache, shared second level cache. And the way that you provided enough bandwidth to that shared cache was by having a crossbar. And a crossbar is kind of an all-to-all network that provides you a lot of bandwidth. But it takes up a fair amount of the area on the chip, and it doesn't scale, right? You could get, in this case, you could get to 8 cores, but if you wanted to go to more cores, then you'd have to come up with a different mechanism, because crossbars are quadratic in the amount of wires you need, right? Because it's all-to-all. All right, so let's talk about snooping cache coherence schemes in the time that we have left, and we will, of course, not finish it today, but we'll come back to it on Thursday. So the idea is that you've got a processor with its individual cache, and the cache. Caches of all the processors are connected by an interconnect, which is just this, set of wires, or a way of communicating between the processors and memory. Okay, so the processor issues loads and stores to the cache, right? And then the cache receives coherence messages from the interconnect, right, associated with other actions that other processes are making. Okay? So a very simple coherence mechanism would be a write-through mechanism, right, where upon a write, the cache controller broadcasts an invalidation message, right, which says, hey, I'm writing address X. If you have address X in your cache, get rid of it, invalidate it, right? So then we're sure that nobody else in the system, no other cache in the system has that address, okay? So what is the problem of the write-through cache mechanism? Yeah.
All the other processors, do they have to keep kind of like polling the interconnect?
Yeah, so assume that the cache is responsible for that, right? So the cache kind of decouples the processor from the interconnect. So the cache is always looking at the interconnect saying, hey, is there an invalidation message on the interconnect? If so, let me check my cache. Do I have that address? Yes, invalidate it. No, ignore it. Yeah, what's the problem?
If two processors broadcast the invalidation for the same address at the same time?
Well, somebody has to win, right? Right. So assume that this interconnect only allows one message at a time, and there's a winner, right? Okay. So the problem with this is the write-through cache, right? It says every write that the processor makes has to appear on the interconnect. Again, we're going to run out of bandwidth. So this is a low-performance solution. So what we want then is how do we do coherence with write-back caches? Okay? So first of all, we're going to change this interconnect to a bus. Okay? So a bus has two very nice properties. Does anybody know what they are? Yeah.
They're really wide.
They're wide because they have lots of bandwidth. But from the point of view of coherence, what properties do buses have?
That's not allowed to remember at the same time.
Right. So there's only one transaction at a time. So somebody asked about that, right? So bus, by definition, one transaction at a time. Not true for a ring, not true for an arbitrary network, but true for a bus. One transaction at a time. So what does that mean? When somebody says one at a time, what's the first thing that comes to your mind? Serialization, right? So the buses act as a serialization point, okay? What's the other benefit of a bus? kind of like the air in this room. It's a broadcast medium, right? One processor says something and everybody else hears it. All right? So, two properties of a bus. We have broadcast and serialization. Okay, so what we want then in our write-back cache is we want to make sure that whenever a processor is writing a value, that it is the only processor in the system that is actually allowed to write. Okay? And so one way of doing that is by indicating exclusive ownership of the cache line. And let's assume that exclusive ownership is indicated by having the dirty bits set, right? So what we need to ensure, though, is that only one cache in the system can ever have its dirty bits set at any time, right? Otherwise, we're going to violate that invariant that says, hey, there's only one processor in the read-write epoch. So we can only have one. Okay, so we need a way of enforcing only one, right? And the way of enforcing only one processor at a time is in the read-write epoch is called a cache coherence protocol. So it maintains the cache coherent invariance. It assumes that there's some hardware logic that's going to look at loads and stores made by the local processor and messages from other caches on the bus. Okay? So in an invalidation-based write-back protocol, which is what we're going to describe, there's a set of key ideas. Somebody asked about what other state is in the metadata for the cache line. Well, you need some cache coherency state, right? And the idea is that you're going to have some cache coherency state, and you're going to be able to allow only one processor to be in a certain state at any one time. And you need to be able to tell the other processors to not be in that state. Okay? So let me see. I think we have time to just introduce the idea. Right? So we talked about dirty bit, and we talked about the fact that we need some cache coherency line state. Let's talk about a protocol, cache coherency protocol, for a write-back invalidate-based cache, right? So key tasks of the protocol: ensuring that one processor can get exclusive access for a write, and locating the most recent copy of the cache line, based on the cache line's data on a cache miss. Okay? So in the MSI protocol, there are three states: modified, shared, and invalid. Hence the name. And in invalid is the same as, the cache line is not there. Shared is this state where multiple processors can only read the line, so read only. And modified, the line is valid in only one cache. Or it's in what we've been calling the dirty or exclusive state. Okay? So invalid, the cache line is not there. Shared, read only. Modified, valid in exactly one cache. All right? So we have two processor operations: processor read and processor write. Three coherence bus transactions, right? So these come from the bus. So these come from the processor read and processor write. And then bus read exclusive, bus write back come from the bus. And these are caused by actions of other processors. So bus read means, hey, give me a copy of the cache line because I want to read it. Bus read exclusive says, give me a copy of the cache line because I want to write it. So first of all, before I can write it, I need the whole cache line, but I'm going to write it. And then bus write back says, hey, this is a cache line that was dirty in my cache that I'm writing back to memory. Okay? So keep this in mind. We're going to continue with the story on Thursday and talk about how exactly we maintain coherence using these 3 states and these actions.